Hello, my name is Davis Binger, and today we will look at the Quiz 1 solutions. Quiz 1 consisted of two problems. The first problem asked us to find the area in the region bounded by y equals x squared and y equals x cubed plus x squared minus 4x. Problem 2 considered the region R in the right half of the plane bounded by the curves y equals 4, y equals negative 1, x equals y minus 2 squared plus 2, and y equals negative x squared plus 4. In three parts, it asks us to set up an integral that represents the area of the region with respect to the y-axis, set up an integral which represents the area of the region with respect to the x-axis, and part C asked us to compute these values of each integral and compare your results. That is, which was easier, did you get the same value, etc. Problem 1. Find the area of the region bounded by the graphs y equals x squared and y equals x cubed plus x squared minus 4x. The first step will be to find the intersection of the two curves. We equate the functions and solve for x. Subtract x squared from both sides and factor the resulting polynomial to find that 0 is equal to x times x minus 2 times x plus 2. Hence the intersection points occur at 0, negative 2, and 2. We will need to test each interval, that is the interval from negative 2 to 0 and the interval from 0 to 2, to determine which function is greater on that interval. At x equals 1, x squared is equal to 1, and the second function evaluates to negative 2. Hence, x squared is the top function on the interval from 0 to 2. At negative 1, x squared evaluates to 1, and the second function evaluates to 4. So the second function is the top function on the interval from negative 2 to 0. Thus we can set up two integrals which represent our area. The area is equal to the integral from negative 2 to 0, x cubed plus x squared minus 4x, which is the top function, less the bottom function, which is x squared. And we integrate with respect to x. The second integral will be the integral from 0 to 2, x squared minus x cubed plus x squared minus x times 4, integrating again with respect to x. This integral will be a simple one to evaluate as it's just polynomial functions on an integer range. We subtract the x and x squared from itself and cancel it, and we are left with the following simpler integrals. Each integrates by the power rule, and we evaluate using the fundamental theorem of calculus to find out that the answer is 8. Okay, this wraps up problem 1. Problem 2 is a little bit more extensive. Here I've included a graphic for you. It was too big to fit on the original problem statement, but we have a very oddly shaped region, and the shape of this region will lend itself to a better, easier integration with respect to one variable as opposed to the other. So for example, if you look at it with respect to y, then you will have one region. You have a clearly defined top function and a clearly defined bottom function. However, it's unclear what your top and bottom function should be if you want to integrate with respect to x. We'll get to that, but right now let's start off setting up an integral that represents the area as a region using the y-axis. So let me backtrack and look at this picture again. So we know what the top curve is. The top curve will be this x equals y minus 2 squared plus 2. And that's a function of y already. We just need to take this other curve, the y equals negative x squared plus 4, and set it up as a function of y. Then we can integrate from negative 1 to 4, the top function minus the bottom function. So our goal will be to find this second equation as a function of y. So you solve for y, you get x equals plus or minus the square root of 4 minus y. Now this is actually two functions, one corresponding to the positive root, one corresponding to the negative root. It's our job to identify which branch of the square root we're interested in. And it turns out that we're interested in this positive branch. So our area will be given by the integral from negative 1 to 4 of y minus 2 squared plus 2 minus the square root of 4 minus y squared integrated with respect to y. That's A. Now we're going to set up this integral, or the sum of integrals, which represents the area of R, using the x-axis for integration. So this process may seem a little slow and indirect, but let's just start collecting little bits of information, like where these curves intersect each other. That's a good place to start to try to understand our bounds. So we have all of these intersection points. Y equals negative 1, and x equals the square root of 4 minus y. Y equals x squared plus 4, and y equals 4. Y equals 4, and x equals y minus 2 squared plus 2. Y equals negative 1, and x equals y minus 2 squared plus 2. We're going to integrate with respect to x, so we need to decompose this function x equals y minus 2 squared plus 2 into two functions of x, the upper branch being y equals the square root of x minus 2 and plus 2, and the second one being y equals negative square root of x minus 2 plus 2. So the leftmost values for these curves is x equals 2, and we can add the following orange and black lines. So the contours of this graph is a little different than the previous image, but it's the same function. I just used a different graphing software. And we're going to add in this orange line and this black line, and with this we can come up with 4 regions, and each of these regions has a well-defined top function and a well-defined bottom function. So we have R1, and R1 will have the line y equals 4 as the top function, and the line y equals negative x squared plus 4 as the bottom function. R2 will have the curve y equals the negative square root of x minus 2 plus 2 as the top function, and the bottom function will be y equals negative x squared plus 4. R3 will have the top curve y equals 4, and the bottom curve y equals the square root of x minus 2 plus 2. And R4 will have the top curve being y equals negative square root of x minus 2 plus 2 as the top function, and negative 1 is the bottom function. So this is a little more complicated, but if you have a region like this, you need to decompose it into smaller regions where you know the top function and you know the bottom function. And that's what we've done here. Okay, so now we're going to calculate the area of each of these regions, or set up an integral, and basically this is just a repeat of what I described earlier, which was integrating over the bounds, the top function minus the bottom function. So this uses the information we calculated on the first slide of this particular part, which was the intersection points, to calculate the intervals of integration for each of these regions. So R1 goes from an x value of 0 to an x value of 2, and its area will be the top function minus the bottom function integrated over that range. Now, R2 will go from x equals 2 to x equals the square root of 5, and the top function was the negative square root of x minus 2 plus 2, and the bottom function was the negative x squared plus 4. Okay, so we're ready to set up an integral for R3. R3 had a top function of 4 and a bottom function of the square root of x minus 2 plus 2. And if you recall, this point of intersection we calculated previously was had an x value of 6. So we're going to integrate from 2 to 6, the top function minus the bottom function. And finally, for R4, we calculated that this intersection point over here had a x value of 11, and we will integrate from the square root of 5 to 11, the top function, which is negative square root of x minus 2 plus 2, minus the bottom function, which was negative 1. And it turns out that our volume is the sum of these four integrals. Sorry that it's a little cramped there at the bottom of the page. There's a lot of information. Okay, so part C, we will integrate these expressions and get a value for the area. Hopefully they are the same. So we'll integrate first over y. Now we can expand this quadratic term right here, and we will get a nice simple expression. And from here we can use the power rule on each piece. And we will evaluate from the from negative 1 to 4, and we get this pretty complicated expression, but after plugging it into your calculator, you can find that this is 14.213, etc. So that's integrating over y. Now we'll integrate over x. Remember, this was the sum of four integrals. So here's the first two, here's the second two, and we will integrate each of these. So the first one simplifies to just x squared, the second simplifies by canceling some of the constant terms, and we've performed some simplifications on the second two integrals, namely that we have canceled this 2 and this 4 and combined this 2 and this 1. So now we take some antiderivatives and evaluate it on the bounds. Each of these is antiderivatives is a power rule, with the most complicated power rule being a fractional power. So it should be possible to do this integration without much trouble. And we evaluate this expression, and thankfully we get the same value. So that is nice. So I guess the conclusion we should draw is that, hey, it's easier to do one integral than 4. So there you go. Alright, thank you for watching, and as always, you can leave a comment below or email me at binger@math.ohio-state.edu. Thank you for watching, and have a good evening.